Hello, my friends. We're going to calculate the reaction entropy for this reaction right here, and we're going to do so at 298 Kelvin and also calculate it at 398 Kelvin. So let's do this first part. So at 298 Kelvin, this is 1 bar. The superscript means standard pressure, means it's under 1 bar here. We need to add up the entropies for each compound in this reaction. So the reaction entropy at 298 Kelvin. And this M means the molar entropy. Sometimes it's omitted when you're calculating the reaction entropy, so it's per mole. That's going to be equal to the sum of the products times the stoichiometric coefficient times the molar entropy of each product here, minus the sum of the reactants, the molar entropy of all the reactants. So the stoichiometric coefficient times the molar entropy of each reactant here. And so that for this first one, we have a product here, 2 is the stoichiometric coefficient. Now, the molar entropy of iodine, we need to look it up on a table. So you'll need a table of values to look it up. It'd be the entropy here at 298 Kelvin with this molar entropy. And if you look that up, it is 116.136 joules per mole Kelvin. Now we're going to add up for the one for the liquid. So the stoichiometric coefficient is 2. The molar entropy for water on the data table is 69.91. And you got to make sure this is liquid water too. Joules per mole Kelvin, and not of gaseous water. We want to use the right phase that's here. Minus, big bracket here. Now there's 4 for the stoichiometric coefficient for HI, and the entropy is 111.3 joules per mole Kelvin. I always recommend putting in the units, plus just kind of 1 for water, or for oxygen, and oxygen is 41.09 joules per mole Kelvin. Great. So if we plug that into the calculator, you should get, and pause the video, plug it in yourself, but if you do so, you should get negative 32.01802 joules per mole Kelvin. All right, and this makes sense. It's negative entropy because we're going from two gaseous substances in their gas phase to a solid and a liquid. So there's less potential arrangements in here. The entropy is decreasing here. So now we'll calculate it at 398 Kelvin. And to do that, we use similar to Kirchhoff's law, where the molar entropy at some other temperature, in this case 398 Kelvin, is going to equal to the reaction entropy at some initial temperature, 298 Kelvin is usually what we have because that's what we have data for, plus the integral of the heat capacity over the temperature dt. And we're going to go from the initial temperature, 298 Kelvin, to the temperature that we want, which is 398 Kelvin. Oh, and this isn't just the heat capacity, this is the reaction heat capacity, or the change in heat capacity for the products minus the reactants. And we need to calculate that. And so this change in heat capacity between the products and the reactants is just like what we did before. Like we do the sum of the products times the stoichiometric coefficient times the heat capacity of product I of all the products minus the sum of the heat capacities of all the reactants. And this is at 298 Kelvin. And now the heat capacity does change. It is dependent on temperature, so it's not going to be constant, but often it doesn't tell us in this question. So we're going to assume that the heat capacities are constant over the temperature interval. They aren't constant, but often in your questions and exams and stuff like that, you may assume that this is constant, or at least the reaction, the change in the heat capacities between products and reactants are constant. So we're going to look up on the data table what the heat capacity is of each substance at 298 Kelvin. And if we do that, we get, so I'm just scrolling up to there's 2, that's the stoichiometric coefficient for iodine. The heat capacity is 54.44 joules per mole Kelvin. plus 2 waters, and the heat capacity of water liquid is 75.291 joules per mole Kelvin, minus, big bracket, 4 HIs, the heat capacity of HI is 142.3 joules per mole Kelvin, plus the heat capacity of oxygen gas is 23.84 joules per mole Kelvin. Again, pause the video, plug this in your calculator, see if you get negative 285.9 joules per mole Kelvin. Okay, and now that we know what the heat capacity, the change in heat capacity is, we can now plug it into this equation here. So the reaction entropy at 398 Kelvin at 1 bar equals the reaction entropy at 298 Kelvin 1 bar, so that's negative 32.02, negative 32.02 joules per mole Kelvin, plus, now this is constant, we're assuming this constant is constant, so it gets pulled out of the integral, negative 285.9 joules per mole Kelvin, and this is times, now that the heat capacity is gone, it's the integral of dt over t from 298 to 398 Kelvin. And this integral is our friend. The integral of 1 over t is just ln, so this would be ln of t from 298 to 398, ln of 398 over 298. Let me know if you want to see where that comes from. So that's what this is here. So we'll add this plus this times this, plug that into your calculator, pause the video, let me know if you get negative 114.75 joules per mole Kelvin. All right, hope you enjoyed it. Now you can calculate the reaction entropy for a chemical reaction and make sure this reaction is balanced and at a different temperature as long as it's the same pressure. Hope you enjoyed it. If you got some value from it, then feel free to slap a like and it'll motivate me to make more videos.